So, we have now seen pattern mixture models. We have seen general principles of sensitivity analysis. We have seen multiple imputation. And all of that comes together when we apply sensitivity analysis based on multiple imputation. Because really what this chapter 42 is doing is combining pattern mixture model ideas with multiple imputation. In other words, you take an incomplete pattern, and then you impute the data based on a predictive model, but not like the base multiple imputation does. That means you do it starting from MAR. So you build a predictive distribution of what you don't have, given what you have, to put it very symbolically, based on MAR. But here you say, no, I'm going to modify that and apply certain modifications to that predictive model in a well-reasoned, well-understood fashion. One way can be to deviate from ACMV, which is MAR, and go to NCMV, neighboring case missing values, or CCMV, complete case missing values. But you could also say we apply a shift. After people drop out, their blood pressure is going to increase with a certain amount. So we go for the MAR profile, but we add something to it. Or we draw from it, but we assume that after dropout, the variability increases because people go in all sorts of directions. We apply an inflation factor to the variance. Or we can say no. In the active group, people are going to follow the placebo group. That's what we do. So we jump to another group, to a reference group, etc. Carpenter, Kenworth, and Roger have contributed enormously to this area, and a number of these techniques have been implemented in SAS. So, for example, going back to base MI code, we do this now, but we apply a shift. Well, the key tool is, in Proc MI, the MNAR statement. So the MNAR statement is applying, for example, an adjustment, and you say, well, in the ARMD data set, the difference with baseline, that is, at 12 weeks, in treatment group 2, the active group, is following the base model plus a shift of 10. But 24 weeks, then it's 15, and 52, then it's 20. So you kind of add a line, an increasing line to the already conducted imputations. You just shift them upwards. Now, of course, here is an idea. You can actually choose those shifts equal to 0, and then you're back into MAR. And then you can actually gradually deviate from it in very small steps until you reach the point where significance flips from significant to non-significant or vice versa, where it tips over, and that's often called a tipping point analysis. So, while not illustrated here, this can be made part, and various other mechanisms can be made part of a tipping point analysis. A subgroup adjustment, there you say, okay, I apply a missing not at random model, and I'm using FCS here for the record. I'm applying a missing not at random model, but only and as far as subjects are in a specific group. So you adjust towards a certain group. This is, you jump to a reference category. In other words, treated patients are looking like placebo patients in terms of their imputation model. Okay. NCMV. NCMV, we have already discussed it, we've seen illustrations of it, but the thing is, you can apply it to monotone data only. Now, again, there may be the annoying feature, think of the ARMD data set, that there is a small amount of non-monotone missingness. Well, what you then can do is say, okay, the non-monotone missingness, I don't consider serious dropout, etc., because it isn't dropout. People come, they miss a visit, they come again. It's not because they died, because they would not come back, obviously. So what I'm saying is, very severe reasons for missing a visit will typically not apply. Depending on the context, of course. You always have to take the medical context into account. Fine, but that means we could use standard MAR-based multiple imputation to make the data from non-monotone to monotone. Okay. And then in the second round, we have monotone data. Now we apply multiple imputation again, 2 calls to multiple imputation, and we make the monotone data complete, but there we apply identifying restrictions. So this is how you do it, for example, in practice. Look, in the first part of the program, there is impute is monotone. So that is, now you have the 2 uses of monotone next to each other. So here you go from at the top, you go from non-monotone to monotone. In the second, you go from monotone to complete, but here you apply an adjustment and you say, I'm using the NCMV restrictions. Incidentally, whereas in old uses, you had to do all the NCMV programming yourself, it's now just one single option in the new MNAR statement. Okay, says actually prints out what it's doing. It tells you what it's doing. For example, it says the imputed variable diff4 is imputed from the non-missing lesions diff4, and there is missing diff12 and diff52. That's where it identifies from. Diff12 is imputed from observations that have lesion up to diff12 observed and the rest missing. That's the neighbor, right? Diff24 is imputed from subjects who have lesion up to diff24 observed, but the rest missing. Again, that's the neighbor. And diff52, well, that's the last one missing. The only neighbor to that is the complete cases, of course. And then when all is done, we can say, for example, what does it imply now for generalized estimating equations? We go back to the base analysis under MAR. Or we apply a shift. Or we jump to placebo. Or we apply NCMV. And also here we see, well, looking at the treatment effects, for example, at week 52, there is a little bit of variation, but nothing to the point that the conclusions would drastically change. And the same is true if you look at the generalized linear mixed model version. Okay, that brings me to the end of chapter 42.